Picture this. It's a digital locked room mystery. You're deep into a real-time, multiplayer mobile card game, the stakes are getting high, and out of nowhere, your opponent plays a card they literally didn't even hold in their hand. Sounds like magic, right? Or maybe a ghost in the machine? Well, it's actually neither. This was a very real, very scary production bug discovered during an adversarial code review of a React Native app. So welcome to this explainer. Today we're going to unpack exactly how a totally innocent developer shortcut quietly morphed into a massive vulnerability, and more importantly, how you can stop it from blowing up your own codebase.
Right, let's kick things off by calling out a habit we're all probably guilty of. The old, every React Native codebase has a mock_view somewhere routine. You know the drill. We drop in these hard-coded placeholder objects so we can actually see our UI screens while we build them, maybe in Storybook, way before the back-end team has the sockets ready. It's a huge time saver, and honestly a great workflow. But what happens when that dummy data accidentally hitches a ride in your bundle, sitting right there next to your live production code?
Well, let's look at a real-world symptom from an app called Seepcar. This is a social card game built for the Indian market, and it runs on a shared, server-authoritative backend. The engineering team decided to run an adversarial review on it. And by adversarial, I mean they weren't just checking to see if the happy path worked. They were actively, aggressively trying to break the app. And oh boy, did they find something. A player was somehow able to just spawn a fabricated card right in the middle of a game. A card that, according to the server, absolutely did not exist in their hand.
So, let's get into it. Part 1. When fallbacks go rogue.
Okay, so how on earth does an impossible move execute when the server is supposed to be the source of truth? It turns out the culprit was just a harmless little UI mock. See, during a normal game, live state comes in from a socket, maps into a view model, and draws your hand on the screen. Simple enough. But sometimes, a snapshot arrives that the app just can't map. Maybe the round is transitioning, maybe players are swapping seats, or maybe a hand is just empty. When that unmappable state hit, the app panicked and fell back to rendering the mock view. And guess what? That mock view was hard-coded with myTurn true because of course it was. That's exactly what you need when you're building a screen locally. But in production, that fallback didn't just look weird. It essentially handed the user the master keys to the casino right in the middle of a hand.
The logical flaw that allowed this to slip through is surprisingly common. Actually, I see this all the time. The code was using a basic truthiness check on the state payload to decide if a user could take an action. It was basically asking, hey, did we receive something? If yes, cool, let the user play. But it totally forgot to ask the crucial question, is this data actually meaningful yet? Because they just lumped readiness into a generic truthiness check, the app was completely blind. It couldn't tell the difference between a fully mapped, ready-to-play game state and a broken, hard-coded fallback.
Fixing this requires us to be super strict about state. First up, you have to derive your live state completely independent from your raw socket state. Never, ever use one as a fallback for the other. Second, if your state is there, but it just hasn't mapped yet, your UI needs to be honest. Show a syncing overlay or a skeleton loader. Do not show a fabricated mock board. A loading spinner is honest. A fake board is a lie that the user can't see through. And finally, you absolutely must gate user actions on that derived live.myTurn property. No exceptions.
Moving on to Section 2, Silent Client-Side Traps.
So this same audit uncovered a bunch of other hidden gremlins. Take Finding M2, for example. This is your classic async in lifecycle bug. The app had a guest sign-in feature that fired off a command to clear the user token, but it was fire and forget. It didn't actually wait for the clear to finish before mounting the app. Now, on a beefy developer laptop, the clear operation is blazing fast and usually wins the race. But out in the wild, on a slow phone with a spotty connection, the app mounts, grabs the old token before it's deleted, and boom, the user is suddenly logged into somebody else's account. The fix? Literally one single keyword. Just await the clear before mounting. Wild, right?
And then there's Finding M7. So this backend actually hosts multiple different apps, meaning it's multi-tenant. The server was doing its job, correctly blocking cross-tenant reads with 404 errors. But the client app, it was acting like a clueless bouncer. It would happily accept any valid token on boot, even if that token belonged to a completely different sibling app on the same backend. Yes, the server eventually blocked the data access, but the client still opened a session and tried to join the wrong rooms, burning server round trips in the process. The fix here is non-negotiable. A client must reject tokens that don't have its own tenant-specific claim right at the door. If you rely on the server to sort out client-side confusion, you're just going to drown in support tickets that look exactly like server bugs.
The audit also found some smaller, but still super annoying client flaws that show how apps essentially lie to themselves. Finding L2 revealed state setters trying to update dead components because timeouts weren't cleared. Finding L3, that was trapping users in an endless 12-second connecting scrim with zero way out. We've all been there, right? A spinner without an exit button is basically a prison, so they added a quick escape back to the lobby. But finding L5, okay, we really need to zoom in on this one.
Finding L5 is the textbook definition of trading security for convenience. The app's logic was built so that if the device's secure key store failed for whatever reason, it would silently fall back to saving the user's auth token in plain text, just raw unencrypted async storage, all just to keep the user conveniently logged in without a hiccup. Doing that silently in a production environment is incredibly dangerous. The right move here is to strictly limit that plain text fallback to your dev environment only. In production, you have to let the convenience fail to keep the security intact. No workarounds.
Quick side note on this review, the team actually found 6 other issues related to the backend auth, but they purposely tracked those in an entirely separate repository. Why? Because slapping a patch on the client to pretend a server issue doesn't exist is a terrible habit. At the end of the day, a client workaround for a server bug is just a second bug wearing the first one's clothes. If the boundary is broken on the server, you fix it on the server.
Let's move to Section 3, 3 Secure Mocking Habits.
So, what's the big takeaway? How do we actually turn these failures into solid concrete habits for your React Native, Vue, or Swift UI codebase? Because frankly, this applies to any framework where you build components in isolation. Here are 3 things you need to start doing right now. Step 1. Never ever use a mock as a runtime fallback. If your real data is unusable, show a skeleton or a loading state. Step 2. Make your mocks fail closed. We naturally write permissive mocks to make the UI render nicely. But if a mock absolutely has to ship in your bundle, flip its permission flags to restrictive defaults. Setting myTurn false still draws the game board, but it completely neutralizes the danger. And step 3, gate your actions on the derived view, not the raw incoming payload. Because as we saw, just because data is present doesn't mean it's ready.
Finally, Part 4, the adversarial mindset.
Stepping back from the specific bugs for a second, we have to ask, why was this particular audit so ridiculously effective? It all comes down to the mindset. Think about a standard code review. You look at a PR and ask, is this correct? Does it meet the spec? But an adversarial review looks at that exact same block of code and asks, okay, how do I completely break this? What's genuinely terrifying about the Siebgar bug is that by all normal metrics, the code was perfect. The bundle validated, the unit test passed, the CI pipeline was totally green. But the chaos of the real world, an unmapped state that the tests simply couldn't simulate, was all it took to trigger a massive exploit.
And that brings us to a pretty sobering realization. Having a green CI pipeline, that only means you have no known failures. It absolutely does not mean no failures. Almost every codebase out there has placeholders, fallbacks, and convenient little mock data structures just waiting to accidentally slip into the production runtime. So I want to leave you with a question to chew on today. What exactly are your mocks hiding right now?